this afternoon or this morning is from Frank Papworth. Since graduating as a civil engineer, Mr. Papworth has gained over 30 years' experience in concrete technology, durability, research and concrete inspection and repair consultancy. As head of Taywood Engineering, the UK's inspection and repair group, and later as their Pacific Rim manager, he's been responsible for hundreds of major durability-related projects in Europe, the Middle East, Asia and Australia. Today, Mr. Papworth's main interest is as a durability consultant for Bcrc, a role that he has filled on some of Australia's largest projects, including tunnels, bridges, reservoirs, wharfs and desalination plants. Mr. Papworth is also chairman of PCTE, Australia's leading supplier of concrete testing equipment, and SRCP, Australia's leading supplier of anode systems for concrete. He is a past chairman, I believe now, of the Durability Committee of the Concrete Institute of Australia, and his contribution there has been significant. He's involved in the Durability Committee as a National Councillor also, and a Deputy Director of the International Structural Concrete Associates FIB on service life design. Please welcome Frank Papworth.
Thanks. The first thing I'd like to do is acknowledge my co-authors. You'll see Dave Corbett there from ProSec. He's been intimately involved in some of the European developments on strength assessment. Ruben Barnes from PCTE. Joseph White from White Consulting, and he's been involved in the structural assessment once we've done the strength assessment. And Jonathan Dyson and myself that are looking at how to use NDT in strength assessment. The paper today is more of a challenge to CIA. 10 years ago I threw out a challenge on preparing a unified durability commode, and we're nearly reaching the end of the first phase of that, so I thought it's time for another challenge. And the challenge here is to come up with a document which clearly and precisely tells people how to assess structures in Australia. The objectives, like every good consultant, what I've done is I've written the paper, I've written the conclusions, and I've matched the objective to reach the conclusions. The good thing for you is that you're already seeing the conclusions, so if I don't actually reach the end, consider this the conclusions. But the objectives were to suggest why CIA Z11, which is the Concrete Institute's document on how to assess cause, take and assess cause, needs to be updated, and that's because the Concrete Society Technical Report 11, which is on the same topic, and it was a revered document for many, many years, has actually been superseded now because new research findings in BS 6089, which is the UK extension to the European Code on Structural Assessment of Structures, which was also not available when CIA Z11 was written. So that's the first one that we need to consider. Because of CSTR 11 has been superseded, is CIA Z11 on which it's based now out of date? We then have EN 1379 on structural assessment of structures, which has a lot of information on it, but very little of that is actually reflected in AS 3600, where in Appendix B6 you can find some information on assessment of structures. Complementary to 1379 is 12504 parts 2 and 4, which are on ultrasonic pulse velocity testing and rebound hammer testing, and they are fed directly into strength assessment of structures. And we really don't have in Australia documents like those to help us support strength assessment. Although AS 3600 part B6 does say refer to international data, which I don't think is enough really in Australia. And the final bit is to give examples of some structures that we've been involved on, which shows you the variety of approaches that might be adopted. This compares, I've combined the comments in AS 10.12.14 and CIA Z11. 10.12.14 is actually how to take cores on structures, and CIA Z11 more focuses on how to assess them. It has a series of 6 K factors. I'm only actually concerned at the moment with the first 3 because they deal with the actual strength, whereas the second 3 K factors deal with potential strength. Most of the K1 and K2 aren't highly different to what's in BS 12504, But what has been dropped is this thing where you can make an adjustment for test parallel and vertical to the surface, and that needs to be looked at. There are quite a number of differences between the European standards and what we have in Australia in terms of taking the cores and assessing the cores, and one of the big ones is the conditioning that you require, whether you're doing air drying or water curing of the samples before you test your cores. And so these things need to be harmonised in some way, particularly length of time taken for some of them. EN 13791 goes into the assessment of the actual strength from your cores results, and it talks in terms of an in situ characteristic strength, which has to be greater than 0.5 F-C. The important part there is the characteristic strength, and it then goes on to tell you how to work out what the characteristic strength of your cores are. And I say that's important because we're going to see in other places it talks in terms of mean strength rather than characteristic. We need to clearly understand whether the mean is in fact the same as what they're talking about in terms of the characteristic. So there's two approaches there in the European code, and I think it's interesting to note that, remembering I'm now an Australian, not English, so I'm talking from my understanding of an overseas code. BS 6089 says it doesn't follow approaches A or B. It takes a different tack, but it doesn't tell you exactly why it disagrees with what the statistics might be. So it takes a different tack. And then in Australia we have AS 102.14, which gives us a method of assessing strength. I won't go into detail, but it says, okay, we'll work out a Q value based on the number of samples that you've got, and then look up in your table of results, going from lowest to highest, what your Q number is. So you look in the table on the left there. If Q equals 6, you go down to number 6 result and read across and get what your strength is. So that's one way of doing it. AS 3600 Appendix B says there's two ways really. You can do representative testing, and that's where it tells you to follow overseas code. It says if I've got a column here which is the right strength, and I've got a column here of unknown strength, I can test that one and that one, and if they're the same, then they're okay. And it also gives you a method of assessing what the strength of the concrete is. This is where I say EN 13791, alternative 1 method. This is sort of written up in AS 3600 Appendix B6. Alternative 1 says that you can establish a curve for your NDT result, ultrasonic pulse velocity or rebound, versus strength. So you do some testing on some samples, or some core samples, or cylinders rather, and you establish a curve of strength, compressive strength of your cylinder versus your ultrasonic pulse velocity or rebound. And it says you need a minimum of 18 cores of samples to do that. And then you read off your in situ strength measurements based on the lower 90% confidence curve. So be very careful. A lot of people, I think, still read off means and tell me that's the strength, but it's very clearly now that it should be your lower 90% confidence curve. It gives you, well, once you've done that, when you go out to measure the strength of your structure, you need at least 15 NDT results, and it then tells you again how to calculate your characteristic strength. These are very different approaches to AS 3600, I think. Alternative 2 means that you only need 9 cores, and what it says is, well, there's an established relationship between your rebound or ultrasonic pulse velocity and strength. It will be different for your particular structure, but if you do 9 cores and NDT results, you can actually shift that known curve by a certain amount. As it shows you there, you take your results and you shift the curve, and then you only need 9 core results. And then you go on in pretty much the same way as before in terms of calculating your in situ characteristic strength. As I said, BS 6089 throws out those two alternatives and uses a different approach and says, okay, for this relative testing, it gives you a clear approach to say whether the samples from your good column and your unknown column are from the same population, giving you the same strength or not. It's a pretty simple equation there. Now, I mentioned Dave Corbett's been involved in this process, supplying ultrasonic pulse velocity equipment and rebound hammer equipment, and so they've done a lot of testing with their equipment to try and establish this SONREP method. SONREP is just a combination of ultrasonics and rebound hammer results to reduce the variance that you might get in doing your assessment. And you can see there on the top left-hand corner, UPV versus strength. Gives you an R squared of 0.5, not particularly brilliant. It then goes on and gives you the Q value being the new method of measuring rebound. So rather than an R rebound, you now get a Q value. You can go and see the PCT stand if you don't understand the difference, and they'll give you a great explanation. So anyway, Q value, the R squared is 0.9, but then if you combine the two, you're up to 0.93, so you're getting less variance as you go through and add the systems together. And it gives you then a formula for which you can calculate the strength from combined results. And they just point out that it's already a national standard method for taking established strengths in various countries, and is currently being considered by Ryman. Now I'm just going to move on a few jobs. There's a number of other jobs in the paper, where I've just selected a few that make the particular points I want to make. This was a mine in Ghana. They had an approach slab to the crusher. After a few months, the approach slab was already worn out, and the client felt that the strengths may have been the cause. Lack of strength, didn't meet specified strength, may have been the cause. The big thing for me is once you get appointed to do a job, an assessment of a structure, is you need to look at the construction records. That's the first step, look at the construction records. When we looked at the results here, the cube results complied. They gave this correct strength, but they just seemed odd. You couldn't say this in a court of law, but it looked to me as though they'd just forgotten to record all the results that were lower than they should have been. They had a very, very low standard deviation, yet the slump was huge. So we just felt they were suspect. It also seemed that with the very low slumps that they actually had recorded, it was almost inevitable that they would have been adding quite a bit of water on site. So we felt that yes, it was suspicious, so that's led us to say yes, let's do a coring and NDT program. It just sets out there that you can't just go and say let's do 3 cores, you need a proper statistical method of saying how many cores you're going to take, so we did that. That just shows you some sampling on site, three cores from each of the locations that we worked out we required. Just thrown in the resonance test there, because we were transporting the cores a long way. I wanted to do a test on site that would measure the resonance, and then the test when they arrived where they were going, just as a means of proving that the low strength that I felt we were going to get wasn't going to be claimed by the contractor as a transport problem rather than an actual strength problem. The site results we got were showed that it's quite a promising test for doing that sort of thing. And then proper recording of samples. What it showed is that the cores that we were taken, that the strength, this was all done to a South African national standard. I won't go through the details of their passing or failing criteria, but it did show that they had a lot of cores which failed their criteria. So although the original cube results passed, the core results showed that they actually had problems. We also did some non-destructive testing, particularly on this shows a relationship with the rebound hammer for the surface of a slab, and basically what it shows is that you got some very odd results. They couldn't be used to predict the strength, and it's probably what you might suspect, that surface finishing of the slab and various other things mean that it can be very difficult to do things like rebound to predict strength on tops of slabs. So we based everything on the core results. We had enough to do that. We assessed the structure based on the specified 40 MPa concrete as being 25 MPa and the 25 MPa concrete as being 15 MPa. All the structures were checked, and most of them were found to be okay. One stockpile conveyor column was of low capacity. We did then specific coring on that, and it was found to be okay. So having low strength doesn't mean your structure's failed. I put this one in because it shows a major difference between the previous one. They'd taken some isolated cores. I can't remember for what reason now, but they had shown low strength. So the Australian designer was concerned, and so he phoned me up, typical call. Oh, it looks like we have some problems with the concrete, but I think it's just the testing. Can you come and do widespread NDT to show everything's all right? Not asking you to show what the strength is, he wants you to show that it's all right. So, as I said in the last project, construction review, cube results looked reliable. Unfortunately, they actually showed that the specified 25 MPa strength hadn't been met at all. They actually showed that it was really 15 MPa, so reliable but low. The isolated cores confirmed that. A couple of isolated NDT measurements confirmed that. The high fines indicated they'd have had a high water cement ratio, and that would have been the issue. And the client still wanted you to do widespread NDT to prove everything was all right. But we survived. There's no point in doing NDT at this point. You just do a structural assessment based on your original cube results. And everything there was all right except from the primary crusher, where they had problems in the slab and in the columns. That was fixed up with a major steel structure. This is an office tower, 65 MPa specified. There was doubt about the strength in some columns. The test approach was to test some columns where cylinders had been taken and we knew the strength, and then to do the relative testing as specified in the BS. We did 4 test points at various heights, which gave us 16 test points on each of the columns. It showed us that we did them at various heights to show whether there was a significant effect of height, and it wasn't that significant. And you've got a great picture that I have to include. That's a picture of my son doing the testing. A very good technician on site if anybody needs one. That just shows you the control columns. We had to find exactly where the cylinders had come from on the known strength columns, and then we applied that relationship to the strengths of unknown columns. You can't see it there, it's in the paper, and it shows that the elements of unknown strength actually were fine. This was another job which is interesting in that, last job, in that the client wanted to assess the strength but didn't want any cores taken. Because of the unreliability of NDT with different materials, we then got the materials that the structure was made from, made some cylinders, tested those cylinders, so we now had UPV and rebound results for that particular type of concrete, and then we used NDT on the actual elements to establish what their strength was, and that was very successful. I'm not going to go through the conclusions because in fact they are the same as the objectives. Thanks.
We do have time for some questions. Any questions from the floor to Frank? Okay, I've got one for you, Frank. In terms of, we do have one. Anthea?
Frank, given there's various appropriate, perhaps, statistical methods for assessing compliance or comparison to what's meant to be the target or what have you, how much do you think that should be a matter of choice for the person who's going about doing this testing? Because the statistical assessment for a scientist, a scientist should be able to choose an appropriate measure. For example, we've done the T testing, and we've done from time to time the percentile comparison and that type of thing on a basis of assessing what statistical tool is most appropriate to use at the time.
To a large extent, and there I don't think it should be left to choice. I think the option is still help. There's very few people that have real knowledge of statistics. I'm an engineer, I guess that's one I want. But I still doubt that I have the real expertise, because when I have a real job, I go to a professor at the university who really understands the maths, and I learn a little bit each time. I would actually like to see, if what you're saying is there's a number
I agree. I think that would be the best way to go, to choose a couple of options.
Yeah, and in terms of a CIA document, I think we should get a maths professor on the committee that can really answer all of our questions.
Just to add to that, Frank, in terms of the selection of where you sample within the structure, especially coring, obviously there's experience required in, maybe a comment from you on how important it is to get the right part of the structure.
I actually feel that probably one of the best parts about the NDT that we're talking about is that you can rapidly scan the structure and you can say, okay, I've now got all my NDT results I need to make the structural assessment once I've got the correlation. But I've also got the NDT results to show me which areas are weak, which areas are strong, because one of the worst things that people do is they just go to the structure, there's a wall, can't see the difference, I'll take 3 samples and average them, and that's the mean strength. Whereas if you've actually got your NDT to show you weak areas and strong areas, it's a really good first step.
Yep, Rick, Craig?
Right, I just find one of the interesting conversations with that type of analysis is sometimes there are old results that potentially push out standard deviation, when you say using APM 13791 for analysis, sometimes it's higher results using standard deviation. They're potentially very outliers on the basis of this analysis, but whether they're using a lower overall result, I find it's often an interesting conversation at the time talking about why lower overall essentially screen, despite the fact that higher results are driving that lower result.
Yeah, you raised 2 good points. One is outliers, and there's nothing in the Australian codes to rate what an outlier is. And so you immediately have huge discussions on whether that was an outlier or whether it should be taken into account. The European codes actually have how to assess outliers, which is useful. You're exactly right that it can be very difficult, that you do have some high strength and some low strength, but that variability naturally means the overall strength is low, and it is low.
So maybe there's some work there, Rick, to be done on discussing and dealing with outliers, especially this.
As Frank says, the document, if it's enshrined in the document, it makes it a much easier conversation because it is analysis along the lines of guidance documents.
It sounds like some work for the CIA. I mean, as in the Cochrane Institute of Australia, not the other CIA. Can we thank Frank Popper for this?